Okay, so in this video I will demonstrate that how we can generate a tone signal in our computers, and further we can store it in a hard disk by using Python programming. So for that case we need to import some of the library functions which has been imported over here. Then in parameter I set sampling frequency as 8 kilohertz, and signal duration, let's say first we will start with 10 millisecond durations, and both the informations are being printed by these two instructions over here. Then the generate the time vector, basically we have to generate the timestamps for each and every samples. For that case we need to calculate the sampling interval, that is 1 upon fs. Fs is the sampling frequency, its reciprocal is the sampling interval. Now I'm generating the time vector as t. It is basically generated by a method arrange, and there are three arguments. First argument is starting time, and then duration td as we declared as a 10 millisecond, and then the interval size is ts, sampling interval. The informations will be printing by this command. Now we will generate the tone signal. I chose 0.8 as an amplitude, frequency as 200 Hz. Then I use instructions from the NumPy sine. It is in the NumPy package sine function, where amplitude into sine 2 into pi. Again pi is there. Pi, this constant value is there in the NumPy, into frequency into time. Time is a vector. It is a discrete sequence. Then this section will plot the signal, both the signals, in how it looks in a continuous domain, how it looks in a discrete domain. And then finally the task is to store the signal in the computer hard disk, okay, as a WAV file. So for that case you just have to keep it remembered that the sampling frequency must be in the integer format. That's why I just converted to integer. If somewhat it was declared earlier as a floating point, so it will confirm it converts to integer number. Then signal is basically data type converted to float 32 as it is supported by SciPy. By default it is generating as a float 64 bit by these instructions under NumPy package. This has been converted to 32 bit, and the signal has been converted again as a column vector. There is a multiple rows, one column, to make it as a mono signal. And WF, what is WF? I have imported the scipy.io.wav file as a WF. In this particular WAV file we have a method which is write. So we are using this particular write method to store this particular NumPy array as a WAV file in the computer hard disk. So first argument should be the WAV file name, second argument should be your integer sampling frequency, third argument should be your data set which you want to store, and this particular message will print the confirmation message that the data has been stored. Now I will run this code. So restart the kernel and run all of the cells. Okay, so it has been created. Tone signal is stored at current directory. So now we will check it out through Audacity. Import audio file, tone.wav has been generated. So this is the signal of 10 milliseconds. As you can see, the duration is a 10 millisecond. So now what we will do, we will just create a longer sequence. Let's say 10-second audio samples. Again go to the kernel, restart the kernel, and run all the cells. It has been generated. Now we will go for checking the waveform and confirm the frequency from there. So this is 10 second. So now if we just confirm, this is again sinusoid. If we zoom it, so it confirms this is a sinusoidal waveform. Okay, now to check it out, take any one of the sections, go analyze. First of all, you just select any one of the section, go to analyze, click on the plot spectrum. You will see this is spike at 200 Hz. It is a log scale, so it confirms that this is basically a 200 Hz tone signal. Now you can change this particular signal frequency. You can change this particular signal frequency to different one. Let's say I'm making this one 800, okay, or let's say it is to be 500. Control S, save it, kernel, restart it, run all, confirms it is being generated. Go to the Audacity, go to file, import audio, tone.wav, okay, take any section, go for analyze, plot spectrum. So it confirms that the signal is at 500 Hz. Okay, so now we can just reduce that things to make it broader spectrum. So it confirms that this is a 500 Hz tone. So in this way we can generate any tone signal and store it on your hard disk.